The Tower of Hanoi is a mathematical game or puzzle. It consists of 3 rods, and a number of discs of different sizes which can slide onto any rod. The puzzle starts with the discs in a neat stack in ascending order of size on one rod, the smallest at the top, thus making a conical shape. The objective of the puzzle is to move the entire stack to another rod, obeying the following simple rules. Only one disc can be moved at a time. Each move consists of taking the upper disc from one of the stacks and placing it on top of another stack, i.e., a disc can only be moved if it is the uppermost disc on a stack. No disc may be placed on top of a smaller disc. With 3 discs, the puzzle can be solved in 7 moves. The minimum number of moves required to solve a Tower of Hanoi puzzle is 2n1, where n is the number of discs. Origins. The puzzle was invented by the French mathematician Édouard Lucas in 1883. There is a story about an Indian temple in Kashi Vishwanath which contains a large room with 3 time-worn posts in it surrounded by 64 golden discs. Brahman priests, acting out the command of an ancient prophecy, have been moving these discs, in accordance with the immutable rules of the Brahma, since that time. The puzzle is therefore also known as the Tower of Brahma puzzle. According to the legend, when the last move of the puzzle will be completed, the world will end. It is not clear whether Lucas invented this legend or was inspired by it. If the legend were true, and if the priests were able to move discs at a rate of 1 per second, using the smallest number of moves, it would take them 264-1 seconds, or roughly 585 billion years, or 184467440737095516115 turns to finish, or about 127 times the current age of the Sun. There are many variations on this legend. For instance, in some tellings, the temple is a monastery and the priests are monks. The temple or monastery may be said to be in different parts of the world, including Hanoi, Vietnam, and may be associated with any religion. In some versions, other elements are introduced, such as the fact that the tower was created at the beginning of the world, or that the priests or monks may make only 1 move per day. Solution. The puzzle can be played with any number of discs, although many toy versions have around 7 to 9 of them. The minimum number of moves required to solve a Tower of Hanoi puzzle is 2n1, where n is the number of discs. Iterative solution, a simple solution for the toy puzzle. Alternate moves between the smallest piece and the non-smallest piece. When moving the smallest piece, always move it to the next position in the same direction. If there is no tower position in the chosen direction, move the piece to the opposite end, but then continue to move in the correct direction. When the turn is to move the non-smallest piece, there is only 1 legal move. Doing this will complete the puzzle in the fewest number of moves. Simpler statement of iterative solution: alternating between the smallest and the next smallest discs. Follow the steps for the appropriate case. For an even number of discs, make the legal move between pegs A and B. Make the legal move between pegs A and C. Make the legal move between pegs B and C. Repeat until complete. For an odd number of discs, make the legal move between pegs A and C. Make the legal move between pegs A and B. Make the legal move between pegs C and B. Repeat until complete. In each case, a total of 2n1 moves are made. Equivalent iterative solution: another way to generate the unique optimal iterative solution. Number the discs 1 through n. If n is odd, the first move is from peg A to peg C. If n is even, the first move is from peg A to peg B. Now, add these constraints. No odd disc may be placed directly on an odd disc. No even disc may be placed directly on an even disc. Never undo your previous move. Considering those constraints, after the first move, there is only 1 legal move at every subsequent turn. The sequence of these unique moves is an optimal solution to the problem equivalent to the iterative solution described above. Recursive solution. A key to solving this puzzle is to recognize that it can be solved by breaking the problem down into a collection of smaller problems and further breaking those problems down into even smaller problems until her solution is reached. For example, label the pegs A, B, C. Let n be the total number of disks. Number the disks from 1 to n. To move n disks from peg A to peg C, move n-1 disks from A to B. This leaves disk n alone on peg A. Move disk n from A to C. Move n-1 disks from B to C so they sit on disk n. The above is a recursive algorithm. To carry out steps 1 and 3, apply the same algorithm again for n-1. The entire procedure is a finite number of steps, since at some point the algorithm will be required for n equals 1. This step, moving a single disk from peg A to peg C, is trivial. This approach can be given a rigorous mathematical formalism with the theory of dynamic programming, and is often used as an example of recursion when teaching programming. Logical analysis of the recursive solution. As in many mathematical puzzles, finding a solution is made easier by solving a slightly more general problem. How to move a tower of H disks from a starting peg A onto a destination peg C, B being the remaining third peg and assuming TF. First, observe that the problem is symmetric for permutations of the names of the pegs. If a solution is known moving from peg A to peg C, then, by renaming the pegs, the same solution can be used for every other choice of starting and destination peg. If there is only one disk, the problem is trivial. If H equals 1, then simply move the disk from peg A to peg C. If H greater than 1, then somewhere along the sequence of moves, the largest disk must be moved from peg A to another peg, preferably to peg C. The only situation that allows this move is when all smaller H1 disks are on peg B. Hence, first all H1 smaller disks must go from A to B. Subsequently move the largest disk and finally move the H1 smaller disks from peg B to peg C. The presence of the largest disk does not impede any move of the H1 smaller disks and can temporarily be ignored. Now the problem is reduced to moving H1 disks from one peg to another one, first from A to B and subsequently from B to C. But the same method can be used both times by renaming the pegs. The same strategy can be used to reduce the H1 problem to H2, H3, and so on until only one disk is left. This is called recursion. This algorithm can be schematized as follows. Identify the disks in order of increasing size by the natural numbers from 0 up to but not including H. Hence disk 0 is the smallest one and disk H1 the largest one. The following is a procedure for moving a tower of H disks from a peg A onto a peg C, with B being the remaining third peg. Step 1. If H greater than 1, then first use this procedure to move the H1 smaller disks from peg A to peg B. Step 2. Now the largest disk, i.e., disk H, can be moved from peg A to peg C. Step 3. If H greater than 1, then again use this procedure to move the H1 smaller disks from peg B to peg C. By means of mathematical induction, it is easily proven that the above procedure requires the minimal number of moves possible, and that the produced solution is the only one with this minimal number of moves. Using recurrence relations, the exact number of moves that this solution requires can be calculated by. This result is obtained by noting that steps 1 and 3 take moves, and step 2 takes one move, giving non-recursive solution the list of moves for a tower being carried from one peg onto another one, as produced by the recursive algorithm, has many regularities. When counting the moves starting from 1, the ordinal of the disk to be moved during move m is the number of times m can be divided by 2. Hence every odd move involves the smallest disk. It can also be observed that the smallest disk traverses the pegs F, T, R, F, T, R, etc. for odd height of the tower and traverses the pegs F, R, T, F, R, T, etc. for even height of the tower. This provides the following algorithm, which is easier carried out by hand than the recursive algorithm. In alternate moves, move the smallest disk to the peg it has not recently come from. Move another disk legally. For the very first move, the smallest disk goes to peg T if H is odd and to peg R if H is even. Also observe that disks whose ordinals have even parity move in the same sense as the smallest disk. Disks whose ordinals have odd parity move in opposite sense. If H is even, the remaining third peg during successive moves is T, R, F, T, R, F, etc. If H is odd, the remaining third peg during successive moves is R, T, F, R, T, F, etc. With this knowledge, a set of disks in the middle of an optimal solution can be recovered with no more state information than the positions of each disk. Call the moves detailed above a disk's natural move. Examine the smallest top disk that is not disk 0, and note what its only move would be. If that move is the disk's natural move, then the disk has not been moved since the last disk 0 move, and that move should be taken. If that move is not the disk's natural move, then move disk 0. Binary solution disk positions may be determined more directly from the binary representation of the move number, using the following rules. There is one binary digit for each disk. The most significant bit represents the largest disk. A value of 0 indicates that the largest disk is on the initial peg, while a 1 indicates that it's on the final peg. The bit string is read from left to right, and each bit can be used to determine the location of the corresponding disk. A bit with the same value as the previous one means that the corresponding disk is stacked on top the previous disk on the same peg. A bit with a different value to the previous one means that the corresponding disk is one position to the left or right of the previous one. Whether it is left or right is determined by this rule. Assume that the initial peg is on the left. Also assume wrapping, so the right peg counts as one peg left of the left peg, and vice versa. Let n be the number of greater disks that are located on the same peg as their first greater disk, and add 1 if the largest disk is on the left peg. If n is even, the disk is located one peg to the right. If n is odd, the disk located one peg to the left. For example, in an 8-disk Hanoi, move 0 equals 0,000,000,000. The largest disk is 0, so it is on the left peg. All other disks are 0 as well, so they are stacked on top of it. Hence all disks are on the initial peg. Move 28 to 1 equals 11,111,111. The largest disk is 1, so it is on the middle peg. All other disks are 1 as well, so they are stacked on top of it. Hence all disks are on the final peg and the puzzle is complete. Move 21,610 equals 11,011,000. The largest disk is 1, so it is on the middle peg. Disk 2 is also 1, so it is stacked on top of it, on the middle peg. Disk 3 is 0, so it is on another peg. Since n is odd, it is one peg to the left, i.e., on the left peg. Disk 4 is 1, so it is on another peg. Since n is odd, it is one peg to the left, i.e., on the right peg. Disk 5 is also 1, so it is stacked on top of it, on the right peg. Disk 6 is 0, so it is on another peg. Since n is even, the disk is one peg to the right, i.e., on the left peg. Disks 7 and 8 are also 0, so they are stacked on top of it, on the left peg. The source and destination pegs for the math move can also be found elegantly from the binary representation of m using bitwise operations. To use the syntax of the C programming language, move m is from peg %3 to peg +1 %3, where the disks begin on peg 0 and finish on peg 1 or 2 according as whether the number of disks is even or odd. Another formulation is from peg %3 to peg %3. Furthermore, the disk to be moved is determined by the number of times the move count can be divided by 2. Counting the first move as 1 and identifying the disks by the numbers chapter 0, 1, 2, etc. in order of increasing size. This permits a very fast non-recursive computer implementation to find the positions of the disks after m moves without reference to any previous move or distribution of disks. The operation, which counts the number of consecutive zeros at the end of a binary number, gives a simple solution to the problem. The disks are numbered from 0, and at move m, disk number count trailing zeros is moved the minimum possible distance to the right. Gray code solution. The binary numeral system of gray codes gives an alternative way of solving the puzzle. In the gray system, numbers are expressed in a binary combination of 0s and 1s, but rather than being a standard positional numeral system, gray code operates on the premise that each value differs from its predecessor by only one bit changed. The number of bits present in gray code is important, and leading zeros are not optional, unlike in positional systems. If one counts in gray code of a bit size equal to the number of disks in a particular Tower of Hanoi, begins at 0, and counts up, then the bit changed each move corresponds to the disk to move, where the least significant bit is the smallest disk and the most significant bit is the largest. Counting moves from 1 and identifying the disks by numbers starting from 0 in order of increasing size. The ordinal of the disk to be moved during move m is the number of times m can be divided by 2. This technique identifies which disk to move, but not where to move it to. For the smallest disk there are always 2 possibilities. For the other disks there is always one possibility, except when all disks are on the same peg. But in that case either it is the smallest disk that must be moved or the objective has already been achieved. Luckily, there is a rule which does say where to move the smallest disk to. Let F be the starting peg, T the destination peg and R the remaining third peg. If the number of disks is odd, the smallest disk cycles along the pegs in the order FTR, FTR, etc. If the number of disks is even, this must be reversed. FRT, FRT, etc. Graphical representation. The game can be represented by an undirected graph, the nodes representing distributions of disks and the edges representing moves. For one disk, the graph is a triangle. The graph for 2 disks is 3 triangles arranged in a larger triangle. The nodes at the vertices of the outermost triangle represent distributions with all disks on the same peg. For h+1 disks, take the graph of h disks and replace each small triangle with the graph for 2 disks. For 3 disks the graph is. Call the pegs A, B and C. List disk positions from left to right in order of increasing size. The sides of the outermost triangle represent the shortest ways of moving a tower from one peg to another one. The edge in the middle of the sides of the largest triangle represents a move of the largest disk. The edge in the middle of the sides of each next smaller triangle represents a move of each next smaller disk. The sides of the smallest triangles represent moves of the smallest disk. In general, for a puzzle with n disks, there are 3 n nodes in the graph. Every node has 3 edges to other nodes, except the 3 corner nodes, which have 2. It is always possible to move the smallest disk to one of the 2 other pegs, and it is possible to move one disk between those 2 pegs except in the situation where all disks are stacked on one peg. The corner nodes represent the 3 cases where all the disks are stacked on one peg. The diagram for n+1 disks is obtained by taking 3 copies of the n-disk diagram, each one representing all the states and moves of the smaller disks for one particular position of the new largest disk, and joining them at the corners with 3 new edges, representing the only 3 opportunities to move the largest disk. The resulting figure thus has 3 n+1 nodes and still has 3 corners remaining with only 2 edges. As more disks are added, the graph representation of the game will resemble a fractal figure, the Sierpinski triangle. It is clear that the great majority of positions in the puzzle will never be reached when using the shortest possible solution. Indeed, if the priests of the legend are using the longest possible solution, it will take him 364-1 moves, or more than 1023 years. The longest non-repetitive way for 3 disks can be visualized by erasing the unused edges. Incidentally, this longest non-repetitive path can be obtained by forbidding all moves from A to B. The Hamiltonian cycle for 3 disks is. The graphs clearly show that, from every arbitrary distribution of disks, there is exactly one shortest way to move all disks onto one of the 3 pegs. Between every pair of arbitrary distributions of disks there are 1 or 2 different shortest paths. From every arbitrary distribution of disks, there are 1 or 2 different longest non-self-crossing paths to move all disks to one of the 3 pegs. Between every pair of arbitrary distributions of disks there are 1 or 2 different longest non-self-crossing paths. Let nh be the number of non-self-crossing paths for moving a tower of h disks from one peg to another one. Then, n1 equals 2, nh plus 1 equals 2 plus 3. For example, n8 1.5456 times 10,795.